All right, today we're going to talk about dimension and its implications. Today's session is going to be divided into two separate segments. The first segment is just going to be an overview of three concepts, and the second segment is going to be all about the reasoning behind those particular concepts are true. And once you go over the first segment, I would highly encourage you to look at the second segment because it's going to connect all the dots of all the concepts that we've done so far. Everything from pivot positions to kernel to image to dimension, all of those concepts are going to get interwoven in why these key concepts are true. So for right now, we're just going to go do the overviews, and there's three important concepts to go over today. So the first one is dimension. So far we've internalized intuitively what dimension is, but we haven't formally defined really what dimension is. So to do that, we need a key point. And the key point is that every basis for a vector space has the same number of vectors. And this may seem overly obvious once we go through it. So just as a recap, what is a basis? A basis is a set of vectors that A spans the space and 2 is linearly independent. So as an example, if we have R3, we might use our favorite standard vectors. These will form a basis. And these vectors are going to span the space because if you form a grid with these vectors, you can get to every point in the plane. So that's what spanning means. You can get to every point in your space, not just the plane, but in the space by some combination of these vectors, right? So this first vector just means move some amount in the x direction, move some number of steps in the y direction, and move some number of steps in the z direction. And it's fairly intuitive that that will give you all of R3. In some sense, that's the definition of R3. The second condition says that these have to be linearly independent. So maybe it's the case that you can make some combination of these vectors out of the others. And just looking at them, we can see, okay, I can't get this x value. I can't get the first component from either of these. So that's clearly independent. And the same thing for the y and the same thing for the z. So these are clearly all in different directions. They're going to be linearly independent. So these three vectors meet the definition for a basis. But what this key point says is there's no magical way to have a basis of R3 with just two vectors. And again, this may seem overly intuitive. Of course you need three vectors because it's three-dimensional space and you have effectively three different directions. But in order to kind of be sure of that, you have to essentially try all the different possible combinations of two vectors and show that they don't work. It's not as easy as, it's easier to think that's the case, but maybe there's something we haven't thought of. Maybe there's some crazy way to pick two vectors that will give you all of R3. But what this key point says is you can't possibly do that. And it's intuitive, but it's not clear why that's necessarily the case. So this is one key point. Every basis has the same number of vectors, and we're going to define the dimension of a vector space is the number of vectors in its basis. So this seems kind of overkill. Why are we making a key point to define dimension? Well, because every single vector space has to have the same number of vectors in its basis. it's well defined to say the dimension is that number. There's not multiple numbers floating around. There's a single number that's consistent, and that number is the dimension. So for example, R3, right? R3 requires 3 vectors, so this is 3-dimensional. As another example, we might take the plane described by x plus y plus z equals 0. If we just look at this geometrically, this is going to look like, let me just take a moment to draw this. This is going to be something like a plane that looks like this. It's going to look like this. So it kind of looks like that. It goes to the origin and traces out 2 lines in the xy and xz planes. So it's just a flat plane kind of with slope 1. And it's a plane, so it has dimension 2. But we also know that you can think of this, you can reduce this into row. This is a matrix. It's already in reduced echelon form, and you can find the vectors that span this plane in geometric vector form. And when you do that, it'll look something like this. And so these 2 vectors right here, these form a basis. They're the vectors that form a basis for this space. They span the plane, and also they're linearly independent. I can't create one from the other. And one of the reasons why we create the vector geometric form the way that we do is because it's very intentional that if you use the free variable, that should be a +1. That's a mistake. I'm sorry. But we create the vector geometric form in such a way that the free variables, the only way to get a y is in that y entry. The only way to get a z is in the z entry. And so that makes them linearly independent in much the same way that we are convinced that R3 and the standard vectors form a basis and are linearly independent because there's only one of the vectors that has an entry in the x component, one for the y component, and another one for the z component. So the x, the y, and the z. So we're sure that these are linearly independent, and they just fully describe the solution set of a plane. So this is a basis, and because this has 2 vectors, that means geometrically this is going to be 2-dimensional. So that's what dimension means. Okay, the second concept to go about today are bases for Rn and invertible matrices. So with the previous topic, we know that if you have a basis for Rn, well, Rn requires n vectors. This is n-dimensional. That's almost the definition. So with what we just said is that any basis requires n vectors. So for example, we might have something like, this is our standard vectors that form what we could call the standard basis, but we could pick different ones too. So for example, I might pick something that looks like this. And those are linearly independent. There are 3 of them. We're not sure if they span all of our 3, but I'm just going to let you know that those also form a basis for R3. And one of the key facts that we have that we can get from the previous one, that it requires every basis of Rn requires n vectors, what we can get with this is yet one more key point. And the key point is that any basis for Rn corresponds to an invertible matrix. And vice versa. So one other test for invertibility is that if you have a matrix, so for example, let's say we have the matrix like this. This matrix is only going to be invertible if this or its columns forms a basis. So if you just take the matrix generated by all the columns, sorry, the matrix generated by all the vectors, and just amalgamate the vectors into a matrix, that matrix is only going to be invertible if the original vectors formed a basis for Rn. And another key point is that any n vectors in Rn are linearly independent only if they form a basis. So this is combining two concepts together. We have linear independent and basis. And if they form a basis, they have to be linear independent, but it's not clear that they actually span the whole space. So one thing we'll explain in the why video is why is it this goes the other way. But if I take three vectors in R3, if they're linear independent, they're going to span R3. That's what this says. And by this means the corresponding matrix has to be invertible. So a lot of these dots are getting connected, and it kind of gives us different ways of thinking about vectors versus matrices versus vector spaces versus bases and so on. But these are the two key points to take away. If you want a way to create a grid of Rn, like up here, all you have to do is pick any 3 independent vectors. If you wanted a grid in R10, all you have to do is find 10 independent vectors. The last key concept is called the rank nullity theorem. And this may seem like a weird combination of words. Just a reminder, what's the rank? The rank is equal to the number of pivot positions and the nullity. We're going to kind of do this from a backwards perspective. This is actually the dimension of the kernel of a matrix. That's what the nullity means. This is the dimension of the kernel. This just means the dimension of the kernel of A. And keep in mind that, I'm going to draw a picture in a second, but the rank and the number of pivot positions, each pivot position gives you one vector in the image of the basis. So this is actually equal to the dimension of the image of A. And it turns out, and I'll draw a picture of just to illustrate this in a second, this is going to be equal to the number of non-pivot positions. Number of missed pivots, maybe that's a better way. So let's just draw a little picture, do a quick example. So let's take a matrix that looks like this. And if we row reduce this, what's going to happen? So when we row reduce this, we're going to get 1, minus 1, 0, 0. So we had a pivot here, but we missed a pivot here. All right, so this pivot position from before tells us that the image is going to be spanned by just that vector. So the image of this matrix is going to look like just the line generated by 1 minus 1. Oops. Yeah, 1 minus 1 generated by that one. It's going to be generated by this line right here. That's what the image looks like. And so this pivot position contributed 1 dimension to the image. In contrast, what does the mispivot mean? The mispivot means that if we solve AX equals 0, this mispivot right here is going to tell us that we have 1 free variable. That free variable is going to come along with some vector. In this case, it's 1, 1. And now this mispivot position gives us a free variable, which gives us a vector. And that vector then is going to give us 1 dimension in the kernel. So the kernel is going to look like this. So this is the kernel of A. So every missed pivot or non-pivot column contributes 1 dimension to the kernel. So this is, we're going to get a line that looks like this. And maybe to get a clear before and after picture, what's going to happen? Let's go ahead and create a clear before and after picture. So this is going to be our before and after picture. So let's align these a little better. All right, so if we actually took all the pictures of this matrix, all the vectors that we wanted, what's going to happen? So we're just applying the matrix here as 1 minus 1 minus 1, 1. And so the red vector is going to be right here. The green vector is going to be right here. And the blue vector turns out to get smashed right onto there. So notice that because the blue vector, say minus 1 minus 1, lies on the kernel, it's in the kernel, it's going to get smashed after it's transformed to this. So we actually started with a circle, right? We actually started with the whole plane, but just for sake of illustration, you can think of it as a circle, and anything that lies on the line, the green line, the line generated by minus 1 minus 1, that's what gets smushed to the image. So we started with a 2-dimensional thing, and one of the dimensions is lost. So we end up with 1 dimension left. That's 1 dimension in the image. And that 1 dimension that we keep is encoded by the 1 pivot position. And we lose 1 dimension. 1 dimension gets smushed down to the origin, and exactly the dimension that gets smushed down to the origin is the kernel. So altogether, what does this say? Because every column in a matrix either is a pivot or is a non-pivot, what we get is that the number of columns of our matrix, and this gives us the rank nullity theorem, the rank nullity theorem says that the number of columns is equal to the number of pivot columns plus the number of non-pivot columns. Okay, that sounds obvious, but really where this really shines is the number of pivot columns is just equal to the dimension of the image of A, and this is also called the rank of A. And the number of non-pivot positions is the same thing as the dimension of the kernel of A. So whenever you're doing your work, whenever you find the kernel in the image, the total number of vectors that you get in both of your answers should always add up to the number of columns you originally started. So in this case, we got a one-dimensional object for the image and a one-dimensional object for the kernel, right here, this line. And so 1 plus 1 is sure enough the number of columns that we started with. So this is the rank nullity theorem.